Hey all, welcome to part 4A of this presentation. I know you must be confused why this is not part 5. Well, I thought I could cover both the interface definition and the server architecture in 5 minutes, but it turns out I need more time. So here we go. We'll go into a little more detail on the code in this segment, into detailed design rather than just architecture. I chose to go into more detail as my project colleagues found it a little more challenging to understand this part of the code. So let me address the problem first. Here's the fundamental problem we're trying to solve. Some tasks could take a longer time to perform than we expect of computer systems these days, where you expect like immediate response. We do not want the server to be non-responsive while the computer performs these tasks. Sometimes this approach is called asynchronous procedure calls. This approach is not necessarily new. For example, here is a code from a book from 1992. The use of the remote procedure call technique as a means for distributing the execution of a program between several machines has become well known and widely used. It provides an easily understood and reliable model for distribution. At the same time, while distributing the code execution, in its synchronous form, it limits the degree of parallelism that can be achieved by an application. An initiating process is not necessarily made to wait while a remote server performs some subsidiary part of the work. Issues involved include the need for the arrangement to be transparent to the user and considerations of reliability and error recovery in the presence of system failures. So you can see some of the concerns there. This is from more than 25 years ago. So these days it's pretty common, but it's still a little bit tricky to program. So here we are not just talking about asynchronous calls remotely. We also want to consider async calls within the server for hardware interfaces and other functions. 3 types of procedures would benefit from asynchronization in our system. 1, hardware access. For example, GPIO operations reading data from our humidity sensor can take a few seconds. 2, storing data. For example, we want to write the most recent data at a regular interval to the files. 3, aggregating time series data. We want to average, find maxima, and so on from the data. In addition, as we are controlling or accessing data from across the globe, asynchronicity is also desirable due to network delays. This is the more remote procedure call part. Rather than using any framework, we use the more basic threading primitives to achieve asynchronicity, and I chose this design due to the simplicity and flexibility. I'd be honored to discuss if you have seen or know of better approaches here. And also, there could be a better name for this method than asynchronous calls that I've used here. As an illustration, let me take the example of reading from the temperature and humidity sensor. By the way, the temperature and humidity sensor I have used is compatible with the Adafruit DHT22 sensor. I relied on an excellent tutorial to use the sensor for a simple program for a hardware test. The tutorial by Emmet in PiMyLife.com is linked in the description. On top of this, we built the threading. In this example, the temperature and humidity sensor is connected to GPIO 4 of the Raspberry Pi. It uses a timing-based digital transfer technique that is handled by the Adafruit DHT library on top of the RPi GPIO library. However, it can take a few seconds to get a single reading that the hardware drivers check for consistently before returning the data. Let us see the code in the rpi_hardware.py file that handles the asynchronous reading of sensor data next. Quickly, the abstract RPi hardware class implements items that are common to the mock as well as actual hardware. Getting the list of plants is needed both for the mock and the real hardware. In this implementation, the mock hardware does not have any code at all because There's nothing extra it does on top of the abstract class at the moment. In the actual hardware, the code creates a thread to read data continuously for each plant. Now let's look at the code in the temperature and relative humidity thread class. It has a single memory location, or a bank, where it stores the more recent sensor readings and timestamps. And it initializes the hardware interfaces. When the thread runs, the code updates the memory location and sleeps if the allocated time is not over. By allocated time, I mean the sampling time. If a request for real-time temperature and humidity reading comes in, the code only returns the contents of this memory location without actually accessing hardware synchronously. Next, we will see how a similar coding pattern is used to make the client calls asynchronous as well. That's in part 5. Thank you.